like this. We say chemistry 2 like this time. Do you get it? It's like when you're writing the oxidation state in the parentheses to tell whether it's iron 2 or 3 oxide. It's one of the dorkier jokes that gets mentioned perennially. But okay, so this is chemistry 2 time for the first time in 2 years. We're talking today not about chemistry 2 time. Well, we did, and now that's done. We're talking about the gas laws. Tell me the names of the gas laws, please.
Gay-Lussac.
They're named after people. Yes, one of them is called Gay-Lussac.
Boils. Hey, Lily, let me learn in my own class, please. I can't remember.
Boyle.
Charlie.
Just Charles.
Charles.
And we can either say, now listen, I'm going to teach you a little bit about apostrophes. So when we make the word Charles possessive, it depends on if you want to say Charles's, which is an okay way to say it, or Charles. If you want to say Charles, it's just that. If you want to say Charles's, it's that. Like if you wanted to talk about the wounds of Jesus, you want to say Jesus's wounds, or do you want to say Jesus' wounds? It depends. That's where you put the apostrophe, depending on. And I think English majors can put a comment in here, but I think that either is acceptable. If the person or object's name already ends in S, you can either make it possessive by just putting an apostrophe, indicating that you should pronounce it as Charles' law, or apostrophe as Charles's law. And I can see of both sides why you may or may not want to do that. Because we have the 3 laws named after gentlemen are Gay-Lussac's, Boyle's, and Charles's. Let's now write what things these relate. So the objective, which I should remember to write down the objective. The objective is, it's on earth science, so I'll have to remember this. It's relate, you have it in your lab maybe, relate temperature and pressure and, it is stapled on the board. It is document changes in gases due to pressure, volume, and temperature changes. So we're going to have to remember that. Document changes in gases, spelled, I think, in America with one S-E-S, so there's actually 2 S's, and then in Britain, I think it's G-A-S-S-E-S, which I put it here. Document changes in gases due to temperature, pressure, and volume changes. So we're relating the changes of one of those things as the others, or one of the others changes. So which two variables, which quantities are being related by Gay-Lussac's law? Pressure and temperature. Boyle's?
Volume and temperature.
I think it's pressure and volume. And then Charles's? Volume and temperature. So this is the most chaotic way to memorize these, but the way I memorize them is that Boyle's sounds like it would be about temperature because of the word boil, but it's not about temperature. And then Charles's is about temperature. These ones are, I don't know why, but these ones are more usually talked about. Maybe it's because this one has like a weird word that in America we don't want to say. I don't know if that's true or not, but he is French for one thing. But this one relates, I don't know, I remember this one because of a propane bottle. You know propane bottle. Alexa, you know propane bottle. Mm-hmm. This is a pretty good drug, propane bottle, if I do say so myself. But as the pressure is let off the propane bottle, like by being used in a grill or whatever, this actually becomes really quite cold. When you let gas pressure decrease, it becomes quite cold. Even if it's a warm day, when you let the air out of a tire, it always seems cold. Not only because of the movement of the air, although that does usually make things seem cold, but also seems cold because it is cold because of Gay-Lussac's law. This guy, very, very lightly, it's almost empty, seems cold, especially if it's upside down, because we're reducing the pressure. That's Gay-Lussac's law. Also, when you air up a bike tire with a bike tire pump, one of these, it gets hot. Or one of those balloon pumps. We have to go get a balloon pump. And I need some balloons too, actually, for this whole thing. If you air up a balloon with a balloon pump, it gets hot. The pump itself gets hot. And people oftentimes think that's because of the friction between the plunger and the pump and the outside of the pump, and some of it is, but mostly it's because of Gay-Lussac's law, that by increasing the pressure, it also increases the temperature if the volume stays the same. And so that's the other thing. We can have a column here called what stays the same. So, because one of these, for each of these laws, one thing has to stay the same. So if we're relating pressure and temperature in Gay-Lussac's law, what are we assuming stays the same? Volume. In Boyle's law, if we're relating pressure and volume, what must stay the same? Temperature. And in Charles's law, if we're relating volume and temperature, what must stay the same? Pressure. So here I have a really quite cold balloon. And I have a pump. And if you blow it up, you can feel, well, it's still kind of cold because it was in a cold room. You can feel, I hope you brought me more balloons, Lily. You can feel that the pump is a little bit warmer now. What should, if Gay-Lussac's law is right, what should this feel like as I let air out of the balloon? Try it. I used a pump, so you can even put it right in your face and you won't get germs because the pump doesn't have as many germs as my lungs do. What's it feel like? Cold! What's this feel like? You can barely feel it anymore. It was pretty cold when I started, but you can feel it. That's kind of warm, right? It's warmer than the end of it. Yeah, I do want my balloon back. Okay. However, I would not recommend memorizing any of these because there's a better one. Okay, cool. That's nice.
Which one's Gay-Lussac's? Don't look at your notes.
I will say I would memorize the names of these because that, as a concept, will be tested. But this is the equation I would actually memorize. This is called the combined gas law. It has to do with physics. This class is called chemistry too. I would memorize this one. It's called the combined gas law. What's one thing you notice about the combined gas law? Okay, it's a combination of, we didn't even write the equations for these, but it's a combination of all three of the named gas laws. What else do you notice about it? What might I solve for? Okay, it's an equation. Yes, they are equal. What is something I might solve for using the combined gas law? What's a quantity for which I might solve using the combined gas law? What about a gas? It's probably not. Pressure, for instance. Let's say I'm trying to solve for pressure 2. I can solve for any of them, but can I use this equation as it's written to solve for any of them? No, basically I'm never trying to solve for the quantity P2 times V2 divided by T2. I will always, in other words, always have to, what? Manipulate. I will always have to manipulate this. I will always have to manipulate this. And be really careful when you're solving for T2 or T1 because they're on the bottom. The easiest way probably to do that is to get them in the top first and then divide everything else over. Another way to do it is to get everything away from it and then flip both of them because it'll always, people forget that when you remove everything from the same side, for instance, as T1, right, you divide by P1 and V1, T1 still stays in the denominator. Now you've solved for 1 over T1 equals P2 V2 over T2 P1 V1. And you don't want to solve for 1 over T1, so you flip both, and then you end up with T2 P1 V1 over P2 V2 equals T1, for instance. You have to, another thing you have to remember, always use what temperature scale and why? Kelvin and why? There are no what's in the Kelvin temperature scale. Okay, that's true. There are no degrees because it's not starting from a random, that's what the degree symbol for both Fahrenheit and Celsius means, is that they're starting from a more or less random, not random maybe, but arbitrary, a human being set starting point is what the degree symbol means. But Kelvin doesn't have that because it starts where? What's 0 in the Kelvin scale? Absolute 0, which is the lowest amount of energy an object can possibly have, and therefore can we ever have a negative Kelvin temperature? No, never a negative. That's why we always use Kelvin, because if we use Kelvin, we're not always working with positive numbers. We are always working with positive numbers, which is great because if we use a temperature scale that does have a negative, we might end up with a negative pressure, which is a physical impossibility, and we might end up with a negative volume, which is a physical impossibility. So we'll always have to manipulate this, and we'll always have to use Kelvin. I'm going to put it approximately next to this because we could also use the English version of the Kelvin scale, which is called the Rankine. And that has 0 at absolute 0, just like Kelvin does. But instead of using Celsius increments up from absolute 0, it uses Fahrenheit increments up from absolute 0. Never does that come up in this class. I would imagine unless you go to like engineering school, it probably would never come up. Engineers are really, really prone to wanting to use English measurements for things for some reason, even though it's worse. Carpenters too. Carpenters, however, generally don't use the combined gas law. Another equation we need to know. The next thing is this one. This is usually an easier equation to use. Sometimes there is some overlap. Some things where we want to use this one, we can use this one, and vice versa, but usually it's going to be distinct. Generally, we use this one when we have a before and after. The ones are before, and the twos are after. And generally, we use this when we have one set of conditions. When we have one set of conditions. P here is, there are different scales we can use for, or different measurements we can use for pressure. We'll talk about them in a second, but V is volume. Lowercase n is amount. Yep, exactly. N, what unit do we always use for that? To my knowledge, we always use moles. Okay. R, we'll talk about in a second, but capital T is temperature. What must we use for temperature? Kelvin. R is the ideal gas constant. And since it's a constant, we have a known value for it. In fact, your book gives 3 known values depending on if you want to use pressure measured in pascals, atmospheres, or millimeters of mercury. The one I would memorize is 0.0821 liter atmosphere over mole Kelvin. That's the one I would memorize. That's probably the one we use the most. Volume then, of course, in liters. And pressure can be in millimeters of mercury, pascals, or atmospheres. But for this number to work, we like it to be in atmospheres. I'll put or millimeters of mercury or Pascal. Or kilopascal, really. You could use the same gas constant with kilopascal, just divide it by 1,000. Your book has a little section about how to find the density of a gas based on its molar mass. It's really just a manipulation of this, because you see we have the amount in moles can easily be converted to a mass. We have a volume. Everything else being equal, cetus paribus, we can find the density of a gas too. So it's really, as I say, a manipulation. Your page 456 in your book talks about that, but I'll leave that to you. The last thing we need to talk about, and this will be really quite brief, which is good because it's almost lunchtime. The last thing we're going to talk about is gas stoichiometry. I'm going to erase the named gas laws. Oh, I thought Alexis said that. I was like, what? I'm glad you do, Tiana, but Alexis never learned it, so I thought she might have learned it outside of class, which would have been especially impressive. But I'm surprised to even hear you pronounce the word right. Stoichiometry, define for me, remind me, Tiana, of what's the point of stoichiometry?
To get, let me, Alexa, you not Alexa, I don't know what's going to go. So it's like, moles,
Yeah, we're converting from some amount, some measurement of one substance in a chemical equation to a different, or maybe even the same amount of a different substance in a chemical equation. So stoichiometry deals with chemical reactions. We're always going to have a chemical reaction. And the point of bringing that up for the gas laws is that we have a really nice unit conversion we can use if everything is at what we call STP, standard temperature and pressure. If everything's at STP, we can use this very handy conversion factor. 22.4 liters of any, what we call ideal gas. Most gases, no gas behaves ideally, but most of them behave ideally enough that we can use this. 22.4 liters of an ideal gas equals 1 mole. Extremely handy conversion for stoichiometry, because sometimes it'll say a balloon. I want another balloon. sometimes it'll say a balloon, where's my pump? Oh, here it is. It'll say a balloon of, we'll pretend this is hydrogen. A balloon of hydrogen is burnt, and it has a volume of, I don't know, this probably has a volume of like 750 milliliters right now, but we'll say it's a liter for ease of mental calculation. A liter of hydrogen is burnt, or exploded, it's combusted, in an excess of oxygen. How much water is produced? Well, all we would have to do, if it was at STP, which this is not, but if it was at STP, we'd have 1 liter of hydrogen gas, and we can go right from liters of hydrogen gas to moles of hydrogen gas using that equation, 22, or yeah, this relationship. And then we can go right from moles of H2 to moles of H2O, which we would use our chemical equation for, et cetera, so go on like stoichiometry. And then at the end, we convert our moles of water to liters of water, because it would say how many liters of water. And since it's all at STP, if we assume that it is, we can use this as a conversion factor, which is very handy. No. But did you see that one? That was a pretty good trick. STP, the conditions it has to be in are 0 degrees Celsius, which is 273 Kelvin, and 1 atmosphere of pressure. Those are the standard temperature and pressure. And 1 atmosphere, of course, is also 760 torr. I believe that's right. 760 millimeters of mercury, too. Also. Is that right? Yeah, 760 torr, and it's also 760 millimeters of mercury, and it's also 1 point something kilopascal. 101.3 kilopascal, or 101,300 Pascal. Would you feel comfortable doing stoichiometry like this with STP, with the 22.4 liters as one of your conversions? Yeah, I hope so. Where it becomes a little bit tricky is that sometimes you're given a different set of conditions besides ideal ones. And so you really have two choices. You can either use PV equals nRT, which incorporates the moles right into it. P sets the N in PV equals nRT. The ideal gas law is moles. You can use that. Or you can use the combined gas law to convert them from whatever conditions they give you to the STP, and then get an answer, and then convert them back from this to the conditions you were given. Then that's fine too. Either way is fine. That's where there's a strong overlap between do you use PV equals nRT, or do you use combined gas law and stoichiometry. And really either is fine, depending on how you want to do it. Questions at all? Alexa? Yeah. Lilith, questions? Tiana, especially you. You have questions?
Especially Tiana, who's actually in.
Especially Tiana, who's actually in this class.